Good evening and welcome. My name is Jill Pfeiffer. I'm the director of ICERM, the Institute for Computational and Experimental Research in Mathematics, a National Science Foundation institute at Brown University. ICERM is delighted to be co-hosting this public lecture with Johnson and Wales University, and we also gratefully acknowledge the support of the National Science Foundation and Brown University. It is my great pleasure to introduce the extraordinary applied mathematician and physicist who represents the mathematical side of tonight's lecture. Dr. Michael Brenner is the Glover Professor of Applied Mathematics and Applied Physics and Harvard College Professor at the Harvard School of Engineering and Applied Sciences, as well as the Area Dean for Applied Mathematics. He completed an undergraduate degree in math and physics at the University of Pennsylvania and went on to earn his PhD in physics in 1994 at the University of Chicago. He is a 2014 Fellow of the American Academy of Arts and Sciences, and he is a well-known educator and lecturer. Together with his colleague David Weitz and chef Ferran Adria, he developed the amazingly popular Harvard class, Science and Cooking. Dr. Brenner's research uses mathematics to examine a wide variety of problems in science and engineering, ranging from atmospheric chemistry, algorithms to help simulate global pollution, to material science, self-assembly and pattern formation, to physiology. Dr. Brenner has a remarkable passion for science and mathematics, and I'm really delighted that he'll be here to share some of that with us tonight. I'm going to turn the podium over to Peter Lemler, Dean of the College at Johnson & Wales, who will introduce our other chief scientists tonight. Peter.
Good evening, everyone. It's my pleasure to introduce an incredibly talented chef and Johnson & Wales University alumnus, Chef Mark Ladner. Mark's culinary career also began in Cambridge at independently owned and operated pizza counters, not quite Harvard University, but it was followed by his formal culinary education with us at Johnson & Wales in Providence. After graduating in 1990, he moved to New York City and worked with several well-regarded restaurateurs before teaming up with Mario Batali and Joe Bastianich to open Babbo as its sous chef in 1998. Mark cooks a sensible interpretation of modern regional Italian-American cuisine, or cucina newyorkese, and over the past 17 years, he has continued with the group as chef partner, opening such restaurants as Lupo Osteria Romana, Otto Enoteca Pizzeria, and Del Posto. And since opening in 2005, Mark has led Del Posto to a 4-star New York Times rating, the first Italian restaurant to achieve this in nearly 40 years, Michelin star, Relais and Chateau Grand Chef, the Grand Award from Wine Spectator, and the 5 Diamond Award from AAA. This past fall, Mark traveled to the Northeast Collegiate Corridor with his newest concept, the gluten-free quick-service pop-up called Pasta Flyer. Always true to Johnson & Wales, his first stop was our Harborside campus. And this May, we will be honoring Mark for his many culinary contributions to the culinary world and his unwavering dedication to the students of his alma mater by awarding him the honorary doctorate in culinary arts. We couldn't be prouder or more delighted to have Mark join us for this special event. Please welcome Mark Ladner.
Okay, so I guess now it's us.
It's us.
Okay.
It's us, yes.
Okay, let's see how this goes. So this is a quote that I like very much. Mark, I don't know what you think about it, but it's by this guy whose name is Bria Savarin, who, at least to my knowledge, I don't know if you know him better. He was the first person who really wrote a book about the science of cooking, and he wrote this book, which was published in 1826, called The Physiology of Taste, that you can all go home and get online for free. And in this book, at the beginning, he has sets of aphorisms, some of which are not repeatable in public. But the one that I think is most appropriate is this one. He says, "The discovery of a new dish confers more happiness on humanity than the discovery of a new star." And the reason I like this quote is that basically, universities like this one have long lauded and supported the discovery of new stars, but they really haven't paid very much attention at all to the discovery of new dishes.
He was quite a controversial individual for his time, and people still study and try to interpret his writings today.
Some of it is wrong.
I would have to
actually.
agree. You know, food it certainly has a lot more to do with the pleasure of humanity than perhaps a star.
Right. So anyway, that's the basis of tonight's lecture, that there will be words, but there will also be cooking, right?
Some, yes, some.
And Mark will be doing the cooking, so it'll be good. I'm going to cook a thing of M&Ms for you guys. It's not going to be very good, but anyway, we'll see how that goes. We'll see how that goes.
Yeah.
But anyway, okay. So I guess next you're supposed to talk about
packing. Oh, I'm supposed to talk about.
This is you.
Del Posto. So this is the restaurant that I'm currently responsible for. We are currently in our 10th year. And as you can see, it's a behemoth on the west side of Manhattan, 25,000 square feet. We employ over 200 people, which is quite unusual for a restaurant. So yeah, it takes quite a bit of organization, and I'm sort of like the curator of what happens there. I don't find myself cooking as much as I have in the past. But it is important that I make sure that I sort of hold the line on the quality of the experience. So it's a lot of marble, a lot of crystal, a lot of silver, much more of a traditional expression of fine dining than you're finding throughout the world right now. So some of these techniques that we're going to be showing you today are not exactly my wheelhouse, but we thought we'd give it a go. In the pursuit of science.
You don't eat M&Ms?
What's that?
You don't eat M&Ms?
I do. I love M&Ms, but I'm really actually excited to hear about this packing theory.
The M&Ms.
A lot of packing going on today.
Okay, so I just wanted to say a little bit about how I got into this. So as Jill said, I'm just a mathematician. For most of my career, I taught classes that people fell asleep in. You go to the blackboard, you can imagine. Some of you have experienced this yourself, having tried it. But anyway, in 2008, Ferran Adria visited Harvard and gave a lecture called Cooking and Science. And it so happened that when he delivered this lecture, literally at that exact day, Harvard was sort of reinventing their program in general education, which is the idea that every student, no matter whether they study science or not, should learn something about science as part of their education. And we were being pressured to invent ways of connecting with the students so that to learn about science in different ways. And Ferran expressed interest in continuing to work with us, and so we pointed out to him that it would be perhaps possible to teach a class together. At that point, I should say, it's still roughly true. I couldn't cook. I didn't really know anything about cooking, nor did my colleague Dave Waits, for whom we did this with, but we both were very interested in the properties of materials that people cook with. And so we launched with Ferran this class, which ended up we inverted. It was very creative. We changed it from cooking and science to science and cooking. And now today it's changed to mathematics and cooking. And it's all basically the same thing. And that's basically how I got into this. And basically the idea of the class was that every week we discussed a recipe. We're going to discuss this recipe in a little while.
Some foams, yes.
We'll discuss it. And we would get a world-famous chef like Mark to come and lecture. Like, for example, Mark came and lectured a couple months ago.
That's right, yeah, in September.
Right. And the chef would lecture, and the students were fascinated by the chef's lecture, and then we would explain what was going on, and they would fall asleep, but we would declare a partial victory. And then we had this thing that the students we had a lab, and the students would make recipes in the lab to discover the scientific principles, and then they would eat their lab. Which was, and actually, so this is just a little bit of history. When the first day the class was offered, actually Emily was a TF in the class, and so you might remember this. I walked into the Science Center, which is the analog of this, and the entire ground floor was densely packed with people trying to get in the room. The Harvard's newspaper, the Crimson, then sort of ran an interview about this. I just want to show you one thing.
Why did you decide to shop science and cooking?
I'm a freshman, and I'd heard about this, I think even before I applied.
I want to...
There were many other reasons.
Okay.
Because it's something different, and it's something that's like common, like cooking and stuff like that. It's like something fun, but it's related to something that's usually possibly boring, like physics.
What was your first experience in the class?
first experience in a class?
I came on time, like not Harvard time, like on time. And I was all the way in the back.
Because the first day that I tried to go to class, I got like suffocated and trampled.
Anyway, we started from there, and then we made this whole thing up as we went along, and we invented all of these odd traditions, which I don't know if you want to follow today, but they're sometimes fun. So it was a science class, and it was to students who weren't scientists, and so we made this rule, which was every week we would introduce a single equation. Now, actually, Mark is wearing an apron, and I brought several of these aprons in which we put all of the equations. So we had like 12 equations. We called them equations of the week. And basically the deal was whenever we put up an equation, everyone had to clap. And so here's the first instance that this occurred. These must be equal. Oh, where's the sound? It must be the case where motion and sticking are in exact balance. That's our equation of the week. You're all supposed to clap. Okay, and then we had another rule, which will happen today, where we said whenever a remarkable dessert is presented, you will also have to clap. This is a dessert that was presented by Joan Roca from El Cellar Can Roca, which is one of the best restaurants in the world.
I aquesta és l'aigua, que està líquida encara.
And this is the water still in liquid state.
Però quan cau a sobre el meló congelat es congela.
So now the scientists in the room, so you all
Això ho fem a la taula, fa el cambrer a la taula.
Now, we're not going to do that today. We're not going to do that. We're not going to do that today.
I'm in awe.
You're in awe. Okay. So
we have M&Ms, though.
We have M&Ms, right.
There's our dessert.
So, and if anyone is interested in this in more detail, this whole thing is now online on Harvard X. Actually, the second version is about to come out, and we taught it last year, and there were about 100,000 people in the end. Blah, blah. Okay, so now this is tonight. So tonight what we're going to do is this, is what we want to do is show you the spirit of this, right?
Yes.
And what we've done is we've picked a couple of concepts. Since this is a mathematics lecture, we've picked a couple of mathematical concepts that are going to we're going to dance around. I'm going to try, and then what the highlight is going to be that you're going to talk about food.
Okay.
And then I'm going to try to convince you that it has something to do with mathematics.
Okay.
Right? And we should tell them what the concepts are. So this is just in case we get through this. So the first is packings.
Yes.
Because that's what the meeting that's happening at ICERM right now is on packings, right? So we want it to be true to ICERM. Then we're going to talk about phase transitions, elasticity, and diffusion. And these are all mathematical concepts that are critical to cooking. At least that's the idea.
And packing can be found in many of these.
All of these ideas can be found in many of these ideas. Yes. And that's what we're going to do. And so first we're going to start with packing. Okay.
Yes.
So here we go. Packing. So okay. These are gumballs. And so notice. Are you ready?
Yeah.
So those are the gumballs behaving like a liquid because they're not packed. But you see, when they're all in the jar, they're packed. These are M&Ms. Notice, are M&Ms more densely packed or less densely packed than gumballs? More.
More densely.
Why do you think? Less space. Oh, ready? You like to eat M&Ms. Here's flour. Is flour more dense?
I'm trying to do some gluten-free over here later. Yeah.
Okay.
Very, very cautious of contamination.
Now, so it turns out if you go to these people that are sitting in the front row who are at this meeting, what they'll tell you, if you say, what do you know about packing? There's pretty much, you guys are going to kill me, there's pretty much only one thing that they know, okay, which is that it turns out there's one thing that matters. This is it. This is an equation. You all have to clap. Okay. So the equation is, it's an equation for this thing. For some reason, we talk in Greek. I don't know why. It's called phi. It's a volume fraction. It's basically the total fraction of the jar which is filled with gumballs. So I don't know if you've ever entered an M&M contest. Those M&M, no, the jelly bean contest. They're jelly beans.
And you count
the jelly beans in the jar. So if you know this number, then you're in much better shape than if you don't. And it turns out that this number, if for spheres it's about 64%, and for M&Ms it's 70%. And at this point it becomes a solid. So you should go think about that when you enter a jelly bean contest. Now the thing is that the remaining space, of course, is filled with air. Now flour, I don't know. There's a lot of air in this. I don't know. Does anyone bake? Do you measure by volume or by weight? By weight. Very good. If you say by volume, shame on you, right, Mark?
Shame on you.
Because because you're not eliminating the air. Okay, now scientists even write papers about these things. Now I noticed this is a paper about M&Ms. And this has several people who are here at the meeting. Bob Connolly, are you here? Paul Chaikin, there's several people here. actually, that sort of study this. And this is the meeting. Okay, and this is a slide from Sharon. She showed this about packings, and there's just packings. But okay, so the deal is that if it's packed, then you can stand on it. And people say that has a finite elastic modulus. And if it's not packed, you can't stand on it. It's like a liquid. Okay, so now we're going to do a cup of flour. So Mark, did you weigh this cup of flour?
Yes.
So Mark weighed this to be exactly a cup.
Yes.
So now we're gonna weigh it. No, he measured the volume. It's a cup.
Measured the volume, yes.
So okay. This is my cooking. It's 151 grams. Does anybody know the volume of a cup in milliliters? It's 237 milliliters. You should all remember that. Did you know that?
I did not.
237 milliliters. Do you know how much 237 milliliters of water weighs?
I don't.
237 grams. So you know, actually, that all matter has the density of water. It's pretty much true. We can talk about that later. So we asked, actually, so this was 150 grams. So we asked in the Harvard X class, we asked people to please weigh a cup of flour. And the mean was about the same as what we got with your cup of flour, which was about 150 grams. And that remarkably corresponds to a volume fraction of 63%, which is exactly the number that I said. So that's packing.
But less than M&Ms.
It's less than M&Ms. Isn't that weird? That's crazy. I don't think that's understood. This is what people, mathematicians work on. Okay, so now, packings occur, though, in surprising places. This is boring. Was that cooking?
Yeah, it was.
You're a nice guy.
It was a mathematician's.
It was a mathematician's
version.
cooking. Okay, so should we let the audience?
Volunteers.
We need some volunteers. So we need three volunteers.
Who's
Three
ready?
volunteers. Okay,
Right over here?
You. Okay, someone in the back, one of you guys come up. And someone from that side. We need someone from that side. We need to be democratic. We just need three. Just come up. This is crazy. We need three volunteers. Okay, so here it is. Okay, what's your name? Iyad. Okay, Iyad, you get that bowl. What's your name? Marky, you get that bowl. And what's your name? Shaban, you got that bowl. Okay, now Shaban, you have a bowl that looks like of water. Okay, now you have a bowl of egg yolks. And you have a bowl of egg whites. Okay, are you ready? And now each of you, here's the goal. You get a whisk. You get a whisk?
We want you to whisk as furiously as possible.
We want you to whisk as hard as you can. Okay, and we're going to watch to see how well you can whisk. And Mark, you should grade them because you actually are probably the only one who knows how to whisk, right? Okay,
remember, use your wrist and not your arm.
Go.
That's good. Back and forth is the best way. Yeah, exactly. This one's not going anywhere, Michael. This water is not.
He's not whisking hard enough.
It's not going anywhere.
You're
not whisking hard enough.
Come on, what's wrong with you? Okay.
Would you like to take off your coat?
The egg yolk's not doing very well either. Keep going.
It's not
You didn't think
changing
you were
at
going to
all.
get to rest.
That looks pretty good.
What do you think? Have they whisked enough, Mark?
It's a valiant effort.
Okay, we should declare victory.
Okay.
Okay, that's enough.
Okay, victory.
Okay, stop. Okay, but wait, you all get a present.
I'm going to finish the whites.
Congratulations. We should clap for them.
Oh, yeah, you
guys
get
get an apron. You get an apron. Congratulations. You get an apron. You should wear it.
It's a mini skirt with
Okay, but you have to
equations
sit
on
down.
it.
Okay, so the deal is that let's see what happened here. So the water, well, basically that's just water. Look at that. Nothing happened. Damn it. I can't stand it. And the egg yolks, look at that. Mark, does this person know how to whisk?
No, it changed color a little bit.
It changed color.
That's a good sign.
Okay, what about those? Oh, you like that one.
Yeah,
Mark's showing us how to whisk, everybody. Watch.
Both directions. Twice as fast. I'm only human. That's what immersion blenders are for.
Are you done yet? I think we should.
Yeah, we're really close, see?
Oh, he's getting better. Oh,
yeah,
look.
look at that.
That's really great. Okay, so that's awesome. Look what
you
Mark.
saw something, right?
That's amazing. So, do you see what happened? This is amazing, you guys. I don't know. Here, do you have a spoon? Oh, I need a spoon. This is so great. Oh, the water. We're so excited. Look at this. So, look at this. So, you took water, egg white, and you turned it into a solid.
Is that packing?
Yeah. So it turns out that there are. So what happened? So packing. So it's a solid. So you take liquid, and you took air because he mixed air, and it didn't work with the water, and it didn't work with the egg yolk. That's really weird. But it basically made a packing. And in fact, if Mark had really been on his game, Mark, I mean, if you'd really been on your game, it would have looked like that.
Yeah, I know. I think you need sugar as well for that.
No. I'm sure you could have done it without sugar.
But you want to put some of this in there?
No. Let's not bother. I think that's just a waste of time. We're going to put that in the other stuff, right? So I mean, now it's slippery on the stage. We didn't bank on that. So it turns out that what just happened is that this is a packing of bubbles. So it's an amazing thing, which I don't know if you knew, but when you whisk something, you're actually making little bubbles. These are like 10 micron sized bubbles, and the whole thing is filled with bubbles, and that's a picture under the microscope. You see all the bubbles? It's actually a packing. Does anybody know what the volume fraction of the bubbles is about? Were they listening?
It's already falling.
It's about 63%. Maybe it's a little higher. That's pretty cool. Okay, so now we're going to get to the culinary foam. Okay, so Ferran
It's already
Adria.
done.
Oh, you already made it?
TJ already took care of it.
Oh, you took care of the culinary foam. So here's the deal. So Ferran Adria had several, actually many, really great inventions. But one of them is called the culinary foam. And it's sort of, the story goes like this. Suppose you wanted to make a foam. So you see, egg whites are a good way to make a foam. So suppose you wanted, what is this? What is this stuff?
That's just beet juice.
Beet juice. Suppose you want a foam that tastes like beet juice. So one way you could do it is you could pour egg whites in the beet juice, and then you could, but what would happen?
But then it would taste like eggs.
But then it would taste like eggs. But you don't want it to taste like eggs. So what do? So what Ferran realized was that what you do is that you realize what it is, you look at the science of why eggs make foams. And it turns out the reason that it works is that there are these molecules in eggs which basically protect the air bubbles. That says oil, but it should really say air. They take the egg bubbles and they coat them like armor and make them so that they don't, when they collide with other air bubbles, they don't dissolve. And those molecules, if you can just figure out what those are, you can just put those in, and they don't have to be the things that taste like eggs. Anyway, so this is what Ferran figured out. And so he started, and these molecules, they have pictures, they have names, whatever, and you can buy them. And this is called lecithin. And you guys have lecithin, right?
Yep.
It's a soy product. It's a natural soy product. It's a natural product.
It is.
I mean, it's just like, and you think sugar.
It's just a powder.
Just a powder,
They all
is
look
it?
the same.
Powder? Did you put this into the foam? You did.
You did, and just
you
buzzed
put it in,
right?
and then you see what happens is that even beets can be made into a foam. So you should show that. See that?
It looks nice.
Foam. Can I like?
It's pretty
can
stable
I tilt
too.
it? Can I tilt it? Oh. Well, it's just as good as the other foam, and there are lots of bubbles. Can you see the bubbles? If you look really closely, can you guys see the bubbles? It's tons of bubbles. You see how the surface is sort of shiny? Those are bubbles. If we had a microscope, you could see it under the microscope. Okay, was that good?
It's good, yeah. It's going good. This one's not working.
Packings. Okay, now packings actually form throughout cooking. There are many things that you cook. Can we go back to the slide for a second? So there are many things that you cook which are packing. So actually mayonnaise is basically an emulsion of little droplets. So mayonnaise, if you put it under a microscope, you would see the same thing. You'd see lots of little droplets. Whipped cream, the same thing. Cappuccino foam, the same thing. And Mark, I think, is now going to make us a sauce that he serves in Del Posto.
Yes.
Okay, and
that's true. Is this we're doing this this foam thing, yeah?
Well, you're going to make the Del Posto sauce.
Yeah. The sauce first. Okay, so this is a balsamic brown butter. So I've taken 125 grams of whole butter and browned it till the milk solids have separated and burnt, essentially. And then this is just a cheap, fake balsamic vinegar. I put a little bit of salt in that. And now what we're going to do is whisk one into the other. This is an incredibly volatile sauce that I'm not very good at. And I actually struggled quite a bit when I was a younger cook. But you'll find that if you keep the two liquids at about the same temperature and you add them slowly enough, you can create an emulsion that is temporary and quite fickle, but it tastes really delicious. And it's a little bit Italian, even though it's also French. So there we have equal parts butter and balsamic, which I'll show you here. But then, somebody showed me this really cool trick, my friend Wiley Dufresne, which is if you add some water, and then this is a little bit of powder, the same.
Secret white powder.
This
Secret
is
white
xanthan.
powder.
But you can add it to this, and then look at this. This is crazy. And then it's just gonna come right together, or not. I would say mostly not. So here we go. So now it's the same sauce with the powder, and it looks exactly the same.
No, it looks totally different.
Thank you, thank you.
Why do you want it to be an emulsion?
Just so that it coats food more evenly and for a longer period of time, so you can enjoy it.
You mean so it doesn't drip off as fast?
Yeah.
So that means it like flows more slowly.
Yeah, exactly.
It flows more slowly. So you mean if you like make it, if you like take this thing and you like you're making bubbles, right, with this thing? At least in principle, if it were to work.
If it were to work.
And then there'd be lots of bubbles, and then it flows more slowly. So do you know why it flows more slowly? Because it's a packing. I like pouring the M&Ms.
See?
Okay, we're gonna make a mess.
I should have focused more on the science than just trying to will it together, huh?
We didn't tell you we were going to make a mess. Okay, so actually, this is a calculation. I'm a mathematician. I'm supposed to do calculations. So I calculated, this is amazing, you're not going to believe it, the volume fraction of your sauce.
Really?
And it turns out that butter is 70% fat. Just look it up. So basically the volume fraction of fat is 35%, which is less than 64%. And that's not very much. So your problem here, Mark, is that you just don't have enough butter in this sauce.
You think so, yeah?
Yeah. Because if you could increase the volume fraction, it would get thicker.
Shouldn't have cooked it so far in advance, like before we left Johnson and Wales.
Okay, so now we have now we have a fancy interlude. This is you.
Oh.
You're going to do something fancy.
Oh, God. Yeah. Okay, here we go. So this is something that I invented recently, and it's called, I'm decidedly low-tech, and I don't really know how to use these things very well. This is something that I call mozzarella. So it's cream and creme fraiche that has been stabilized and chilled and whipped with some more powders. And now it makes the technique is called reverse spherification.
Yep.
Right. So this is an alginate bath that Dr. Brenner wanted to talk about also. So
it's another white powder.
Again, this is not working. TJ, what do you think? I gotta bring out the big guns. All right.
Oh, wow.
So we're making like a fake mozzarella ball out of obviously super dairy. But what you can do is you can take this and you can float it in this alginate bath, and then it creates this really weird, slimy coating, which then contains the foam and keeps it from deflating. You can also refrigerate this after. And yeah, delicious. Absolutely delicious. So here you go. Ta-da! It's actually quite good, and there's another application that I believe Dr. Brenner is going to explain a little bit later.
Well, I mean, it's great because it's got bubbles in it. You put bubbles in, and then you've put it in this weird white powder broth, which we'll have to talk about later.
Okay.
Okay. Good. So let's see. Next thing. So now we've gone through our first thing. So now we've done packing. So now another idea that mathematicians like is an idea called phase transitions. And so all of you know about phase transitions. You learn about them, especially if you live here. The snow is melting. And that was a phase transition. But you know that basically what happens if you take ice, take ice and you put it on a hot pan. Has anyone ever done this? Is this going to work?
Probably not.
Okay, watch this.
It's melting.
It's melting.
There's no steam.
There's no steam. But it's pretty cool. Look at it. It's making bubbles. It's pretty cool anyway. Watch it. It's becoming a gas. So it's amazing. If you take ice and you put it on a hot pan, it becomes a gas. So now, okay, can I throw this away?
Yes.
So, but now actually contrast that, if you will, with an egg. So I don't know if any of you have put an egg on a hot pan. This is how I cook eggs, Mark. Ready?
Oh my God.
No, but look what happened before.
No.
But it became a solid. So we took a liquid and we put it on a hot pan, and look, it became a solid. You see that? That's amazing. It's exactly the opposite of the ice. What are you so upset about?
It's a mess. Look at it.
What are you doing?
Maybe in the privacy of your own home, but you can't charge money for that.
What are you doing?
This is another version that we're going to make.
You're making eggs.
So we used your favorite device again, this emulsion blender.
Yeah.
And we tore apart all of the albumin and the connective tissues in the egg so that we can make a smooth scrambled eggs here. Does anyone have a whisk that's not too soiled? Awesome. So we're going to cook this gently over a water bath, and we're going to produce scrambled eggs that are smooth as silk. So you take product, you fix it up, and you sell it for profit. That's what they taught me at Johnson & Wales.
You know what? Mark, they also taught you to make bubbles.
A lot.
There are a lot of bubbles.
Everywhere
there are bubbles.
Everything we spoke about so far has involved bubbles. So what's the next
Is it going to work?
principle?
Is this going to work?
Unlikely.
I want to see it. So I want to see these smooth as silk eggs you claim you can make.
TJ, can you do this so we can move on to gluten? So just stir, but don't whip additional air into it.
Is it going to cook?
So there's some air. There's some. It's just a double boiler with the burr-mixed eggs. We added some butter and some olive oil in, and it cooks gently. It takes time, obviously, because there's a lot of space between the heating element and the actual bowl. But it comes out. Try it at home. I highly recommend this version.
Well, I don't know. This is what I make at home.
Nastasia hates it, but I thought you were a vegetarian. I guess eggs are okay sometimes. Okay.
Should we go to the next slide? Back to the slides?
Yeah.
Okay. Eggs. Mark's favorite egg recipe. Okay, now we're at elasticity.
Recipe.
Okay, so now elasticity is another idea. Now, we already talked about elasticity because we talked about the fact that you can stand on M&Ms. But notice there's one thing you can't do with M&Ms that I like to demonstrate, which is they don't hang together when you turn it upside down.
That's true.
Okay, so now Mark, maybe you should talk a little bit about pasta flyer.
Pasta flyer. Oh, so this is a new concept I've been working on, which is quick service, gluten-free, decidedly gluten-free pasta, which you'll see in a moment is quite a challenge. But we felt that this is sort of the inspiration. There's Nonna Farina, our matriarchal heroine in the hills of Abruzzo, if you will. She gets whisked away by some aliens. She was sitting in her empty restaurant. People weren't interested in her slow food. So the aliens brought her to Japan, showed her the efficiency of the Japanese ramen model, brings her to Manhattan, and here you go, Nonna Farina kicking ass in big city USA with gluten-free pasta thanks to some extraterrestrials with some vision. Thank you, Nonna. So we're going to talk about some doughs here, of one of which
But before we do it, I should show them how a mathematician thinks about elasticity.
Yes.
It's terribly boring. Basically, we think of elasticity as springs. And actually, the thing to tell you about this dough that we're about to talk about, those eggs look, I would eat my eggs.
Yeah, me too. Disaster.
Anyway.
Thank you.
Although my eggs are now burning. So anyway, so the thing that's amazing about bread, has anyone made bread? You should all go home and make bread. So if you make bread, so there's this molecule in wheat, which is gluten. Actually, it's two molecules. It's glutenin and gliadin. And basically, these are proteins that basically form cross-links with each other. They stick to each other to form a gel. And then what happens is when you knead them, they tend to line up the molecules. And the molecules, when they're very long and they like to stick to each other by short-range interactions, and that basically gives bread dough its strength. Oh, you're giving out food.
no one wants your eggs.
You're giving out food, what?
What's that?
What happened?
I gave out some scrambled eggs.
Oh, cool. Are they good? Yeah. Oh, okay.
Anybody want these scrambled eggs? We'll put them on top of the cheese. There you go.
Well, at least it's got the cheese.
Yeah.
Anyway, so if any of you have baked, what you learn is that if you want to make the dough stronger, then you either add salt or you use high-protein flour, which gives it more gluten. And there are also ways of making it weaker. You can add fats or oils, sugar, or add acidity. And I think Mark and our friends at Johnson & Wales have made for us 3 types of dough, right, Mark?
Yeah, courtesy of the baking department at Johnson & Wales, we have this one. This is made, they're all the same recipe. One is made for Cup for Cup, which is a gluten-free flour, also developed by a graduate of Johnson & Wales. This is a high-protein bread flour, which is around 13% protein. And then this is Vital Wheat gluten, which is used often in the processed food industry. It's 75% gluten. This is not why people allegedly have celiac disease, which is an immune deficiency disease, but perhaps gluten intolerance could potentially stem from this stuff.
But this stuff is amazing. We were playing this before. You guys all have to make this and go home and play this.
Yeah.
Oh, that was
Imagine that in your lower intestine, huh? Yeah.
But now let's try the bread flour. The normal bread flour. This is actually
this is like regular.
This is regular, but this is high protein, though. You guys didn't even use
this was made set overnight,
ready?
too.
Ready?
So.
Oh, that's pretty good.
You can go.
Check that out. That's cool. Oh, you let go. Go do it again. Oh, that's pretty cool. Okay, now, this is the most amazing thing. This is the gluten-free flour. And by all appearances, it looks the same. Do you see? Doesn't it look like flour?
Allowed to develop.
It's developed?
Overnight.
Overnight. Yeah. Even longer than the regular flour.
Yes.
Okay, so shall we do it?
Okay, ready?
Ready? You guys have to watch this fast. Ready?
1, 2. Oh my God! It's like ricotta cheese. I mean, this is
total. It's like,
how do you make anything from this?
You make pasta out of this?
Yeah. What was I thinking?
How do you do that?
But yeah, I mean, it's a challenge, as you can imagine.
I mean, gluten is really amazing.
It's magic. It's magic, and the amount of ingredients necessary in this dough to poorly simulate.
Right, so you might be curious about what's in the gluten-free flour. So actually, Mark gave me the ingredients in this gluten-free flour for you all to admire. So it has cornstarch, which doesn't have gluten. It has white rice flour, brown rice flour, no gluten. Milk powder, tapioca flour, no gluten. Potato starch, no gluten. But then at the end, there's this ingredient. It's a white powder.
One that made this lovely sauce over here.
It's the white powder that was used in the lovely sauce. It's called xanthan gum. Mm-hmm. And xanthan gum, as you saw in the sauce, it's sort of crappy.
Yeah.
It does bind things together a bit, but that's basically the only thing in there that binds things together.
Yep. And that's decidedly the best version of gluten-free flour really available on the market.
Right, and you compare that with this stuff, and it's just unbelievable. I mean, this stuff basically has the property that, like, air doesn't get out. I don't know if you've ever baked bread.
This is what makes Wonder Bread so delicious right here, this stuff.
They put this in Wonder Bread?
Yeah. Well, because they don't want to take the time to allow it to, ferment and rise naturally.
So they just put that stuff in?
Yeah, it's easy. Yeah. It's science.
No. Science is about letting things rise naturally.
Yeah.
Okay. So now are you going to make a balloon, by the way? Or are we going to skip the balloon?
I think we skipped the balloon.
Okay, we were going to make a balloon, but forget the balloon.
What's the next thing?
So the next thing is now we're on to diffusion. How are we doing the time? Let's see. Oh, are we over? No, we're still good. Yeah. We have time. Okay, so now we're on to diffusion. This is our last scientific concept. So diffusion, okay, so what do all of these foods have in common? So here there are 4 different foods. There's molten chocolate cake. There's ceviche.
Yes.
There's
Which
a
we have
steak.
here.
And this, what is this, Mark? You gave me that picture. I don't
Oh,
know that.
that's a version of rigatoni that is just prior to al dente. So that's clearly undercooked. You'll see the spirit or the soul of the pasta there represented in that opaque white ring. That is how you can identify your pasta as being undercooked.
Huh.
You want it to be firm and al dente, which is the balance of elasticity and plasticity and where they meet, which is difficult to represent with that gluten-free pasta. That's obviously a gluten version. But you want to cook it to the point where it's completely cooked through, but just barely, and that would be considered al dente. So that's actually less undercooked.
So the amazing thing is that all 4 of these processes, as well as this, oh, that's another picture of ceviche, as well as this wonderful spherification that Mark showed us with this, what did you call it, the mozzarella? Mozzarella
Yep.
ball, all basically illustrate the same scientific principle, which is called diffusion. And so now I want to explain to you what diffusion is, and then we'll try to show you how this works.
This is the Searsol.
So we'll get to the Searsol.
Behold.
So diffusion is the following idea. So the question that you have to ask, oh, he's making steak.
So we're going to sear this. Sorry. 30 seconds on each side. We're going to flip it 6 times, and we should come out with something close to a decent steak. But you had other things you wanted to show. Oh, the ceviche, right? Isn't that a similar
Oh, you guys are cooking
example of
ceviche. This is ceviche that, when did you start cooking the ceviche? So, and this has lemon juice. This is lime juice. This is basically tuna, raw tuna, and lime juice. And I mean, do you have some raw, no, not raw tuna, raw salmon, I guess. So here's some cooked salmon. No, this is raw salmon. Oh, he's so interested in this. We're going to wait. I mean, Mark, this is fascinating.
You think so?
Yeah. I mean, we're riveted by it.
I'm
You're
kinda
actually cooking a
bored
steak
already.
this way?
Yeah, you could. You can take it camping. You can take it to the beach.
Is this how you cook steaks at Del Posto?
This is actually just an infomercial right here. So buy a Searsol. They kick ass. They're portable. They're super fun because you get all this cool flame stuff. They have this stuff called Kanthal in them, which is a diffuser that takes away that torch taste so it doesn't taste like crap, even though most of us chefs have been taught never to hold a flame this close to the meat. But it's starting to brown pretty nice. And hey, do you have that cool program that you did?
I think we should watch this first. We'll get to it. There's a lot of science in this, you guys.
So you don't even really have to know how to cook at all to be able to do this. You just need one of these guys to tell you when 30 seconds is up.
Wow.
So how did you plate up the ceviche, TJ?
No, we're gonna first cook the steak and then we'll do the ceviche.
Okay.
Don't you think?
Sure. I'm just afraid it's taking too long. But this is going to be like a kick-ass char, and it's going to be completely raw inside for you paleo enthusiasts. So you can buy one of these through Amazon. I believe they cost $75 for one of the heads. Make sure you use the green canister, or Dave Arnold will kick your ass. Imagine that as the weather gets warmer out there on the green. I don't know if there's laws here at Brown University. You could probably just open your window, your dorm window, and clamp a little sheet tray to the side. We used to use irons in the old days at Johnson & Wales. But don't tell the dean.
Is it cooked yet?
It's an impressive rare. I mean, this is it's like going to Capitol Grill right here. All right, you ready to cut into this?
Yeah, I think we should cut it.
You're going to show your...
I think we need to cut it.
Look at that. It's really...
Do we have a knife?
TJ's
Oh, you put salt on it. Excellent.
We're gonna salt it after so that it doesn't draw too much moisture out.
I mean, this is one of the things...
Salt is crucial for sure.
This is one of the things that makes cooking better than mathematics, because you get to smell it.
Do you like the smell? I was worried we were going to set off the alarm.
Well, it could happen. Are you going to cut it, though? I want to see what happens when you cut it. Oh, you're...
It's going to be really... I'm just trying to make it nice for you, Michael.
I don't eat meat.
Disappointing.
So wait, this is important. This is the exciting part. Look what happened, everybody.
Look at that.
No, but you got to show them this. No, that part. So do you see, look at that. So do you see how around the outside, I need my pointer. You have to focus this. Do you see, look, there's this cooked part around the outside, and then there's the raw part in the inside. And so the question for all of you is, what made the cooked part cook? What happened? Heat went into it, right? So heat somehow made it into the steak. Look at that. Check that out. And you see, if Mark had kept cooking it, if I hadn't been so impatient, this brown layer would have gotten thicker.
Mm-hmm.
And so if you were mathematicians, a natural question for you to ask is if you waited a factor of 2 longer, how much thicker would it have gotten? That's a natural question, isn't it? See? Now,
I'm just admiring my work over here, Dr. Brenner.
But wait, I want to show something else. He's admiring it too. Can you admire this instead? Okay, this is salmon. Do you see this? It's uncooked. Is it sushi grade salmon? Can I eat it? Yeah. Oh, okay. Mm-hmm. This is ceviche. So ceviche is salmon in which has been dunked in lime juice. And notice the outside has changed color. Can we cut it open?
Sure.
Let's see what it looks like. How long has it been sitting? An hour. It's been sitting for an hour.
Oh, look at that.
Oh, wow. Check that out. Here, I need my...
It's almost the same as the...
Check that out. Do you see? There's a cooked layer. Do you see that white thing? It hasn't made it as far in as the heat did, even though it was an hour, you said, as opposed to, what was that? It was about 5 minutes for the steak at most, a couple minutes.
That was only 3.
3 minutes.
Yeah.
So, but this was an hour. But it did, you see that a little bit of cook thing came in. Now, does anybody know why it cooked?
No heat at all.
Does anybody know why it cooked? Yeah. Yeah, the acid, there's an acid. So lime juice is an acid. And you know what an acid has a lot of? It has protons. It doesn't have actually that many, in fact, but it has more than it would if it were just water. And what they do is they move in, and they cause this color change to occur. And if we had waited longer, if we had waited more than an hour, then it would have taken even longer. Okay, this is fascinating, I know. We should go to the slides. This is fascinating. So now let me tell you how this works. So this is through a process that mathematicians call a random walk. And so here's the idea. So you can either be a proton or a hot molecule. Do you want to watch? Maybe do you want to do a random walk? Let's make Mark do a random walk. Okay, Mark, stand right there. Okay, so here's the deal. No, you better stand so you're facing everybody. Okay, so here's the deal. So we flip a coin, and Mark moves either to the right or the left. Go right. Okay, now go left. Right. Left. Left. You're not doing it. Left. Right. Left. So it turns out that's what the heat molecules and the protons do.
Got a bad wheel.
They do exactly that. And the point is it's not very efficient, right? Because you see, he's not going very far. He's going right, and he's going left.
You lose all that inertia.
So it doesn't take that long. And so the point is that it goes right, left. And so that leads to this equation. You know, if he only moved right, it's a much more efficient way to go someplace. See, watch.
That's good.
That was good. But this is not very efficient. And so the length is equal to the square root of 4 times d times t. So if you double the time, the length increases by a factor of the square root of 2, which is only 40%. So it's not very much. And d is a number which is called the diffusion coefficient. And the deal is that what we learned from this demo is that the diffusion coefficient for heat is much faster than the diffusion coefficient for protons. And in fact, if we had done it carefully, which we didn't do, we could actually measure the diffusion constant of protons in water by measuring the thickness of the white layer here, and we could measure the diffusion constant of heat by measuring the thickness of the layer here. Because do you know what the major ingredient of this food is? Water. It's basically all water. It's not much.
Not at all.
Okay. So steak. Oh, and molten chocolate cake, it's the same thing, because the whole point of molten chocolate cake is you just don't let the heat go all the way in, so the middle is molten, so it's all the same thing. So, okay, so Mark already showed us why it's hard to cook a steak.
Yeah.
Right? But the deal is that you see in this, the problem is you need the inside to be at some low temperature, like 60 degrees, and the outside to be at 120 degrees. So actually, in order to help with this, I'm going to just show one little crazy thing. We made this computer program. Here, I want to show you our computer program.
This is really cool.
Well, they may not like it. So here's a little computer program. This was made by a bunch of undergraduates at MIT 2 summers ago. It's called Cook My Meat. You can get it if you sign up for the edX class. It's there. And basically what I did here was I put in Mark's recipe. So it's a 3-centimeter steak. It starts at 23 degrees Celsius. And basically what Mark did was he seared it with the Searzall thing for 30 seconds on each side. And I just said that it was about 150 degrees Celsius. You probably can't contradict that, right?
I cannot.
Yeah, so it's probably reasonable. And I did it like 10 times. I did as many times as you said. You know, you keep flipping it back and forth 30 seconds. And then at the end, you let it rest. And what this computer program does is if you push cook, here, I have to run it again. You didn't hear the sound. And you see, so this is the heat coming on each side. And you see it comes out, there's a brown bit and there's an uncooked bit. And so if you had this at home, you would be a much better cook. Because you could calculate beforehand how your steak was going to be cooked, and then you could cook it as opposed to doing it randomly. Isn't that cool?
Unbelievable.
It doesn't actually work very well, it turns out, but that's a different conversation. I mean, in principle, it's a great thing. Okay, so I think we're almost done. Okay, so here are the equations. You see there are lots of equations. We've only discussed some of them. But there aren't that many. There are only 10.
Not bad for an hour.
No, that's for an entire, that's all of cooking.
Okay.
That's it. Only 10. All of cooking captured in 10 equations. We only did like 2. You should feel gypped. Here's the quote. And then I thought we were going to end with this last cool trick. Right, Mark?
Yeah, it's the low-hanging fruit of modernist cuisine, yeah.
What are these things?
These are, yes, in the spirit of St. Patrick's Day, we decided to find some green peeps. Does anyone know what these are? And this is liquid nitrogen. Don't try this at home, kids, because it's dangerous. So we're going to freeze these, and then we're going to eat them.
So liquid nitrogen makes things that are very, very cold.
And it makes them like more
more
green, which is so cool. St. Pat agrees.
If you were to eat liquid nitrogen, you would burn your mouth. You shouldn't do that. But there's this amazing thing. Do we have a spoon? Oh, that's so cool. They're solid.
They're like
yeah.
Almost.
Have they cooked yet?
I just burnt my finger.
We're cooking with cold. Is this cooking?
I think it is.
Oh, you're wearing gloves.
Yeah.
Do you serve this at Del Posto?
I do not. I don't really do any of this kind of stuff.
People might like it. It is St. Patrick's Day.
You want to try one?
Sure. Has anyone ever eaten one of these?
Who wants a peep? Here you go. Thanks for coming to our demo.
That's it. We're done. We've made enough of a mess. We can keep making peeps, though.
Okay, let's give them a round of applause. That was great. Yeah.
These are pretty good.
Yeah.
And I'll just grab some of these M&Ms while I invite you to line up behind the mics if you'd like to ask Michael or Chef Ladner a question. So please, there's 2 microphones in the center aisle. Please feel free to come.
What's the main ingredient in those peeps?
Air.
We didn't harm any green chicken babies, did we?
No, it's mainly air.
After that, is it corn syrup? Is that the next thing?
Absolutely. Yeah, absolutely.
But if it weren't mainly air, you couldn't put them in liquid nitrogen and eat them because you would burn your mouth.
Or break your teeth, yeah.
Well, you would burn your mouth, actually.
Okay, next side. Please, you can even introduce yourself before you ask a question if you'd like.
I'm Haley. I do a double bachelor's at Johnson & Wales for culinary and baking with a minor in wine. I was wondering, do you guys still do the classes at Harvard, and can anyone outside of Harvard take them?
So the question is, do we still do the classes at Harvard, and can anyone outside take them? So we still teach. It's an undergraduate class at Harvard College that occurs every fall. Like last fall you came, right? And
Yes.
Mark can verify that it exists, right? So, and that people outside Harvard can take. There are 2 ways, though, for people outside Harvard to take the class. One is there's the Harvard X class, which ran last October, but is about to launch again in June. There's a version 2 that will launch in June, which we hope is better. And there's also, the Harvard Extension School we offer the class through the Extension School. And so you can also come take it there. That's also online, although we last month ran an on-campus weekend where people came. It was really fun, and we basically cooked for a weekend.
So you only do it online?
Well, there's the online, and then there's the Harvard Extension one where you can actually get Harvard College credit, and then you can come to campus and hang out with us for a weekend. At least we did that once. I don't know, maybe it wasn't fun hanging out with us, but we made a lot of things.
I don't believe that to be true.
I was wondering if I could have an apron.
Who asked that? We have one more apron. Oh, you can have one. Yeah, yours the last apron.
Good question.
They're a little short.
Go ahead, please.
Hi, I'm Ratyunjay. I'm a graduate student from the Solid Mechanics group. And so being a graduate student, my motto is that whenever I do get time to cook, I just could cook tons of food. So, but the only thing I've noticed is, and maybe you'll be able to comment much better on that, if I take a recipe for 1 serving and then I decide to make 4 or 5 servings of that, it almost all the time doesn't scale linearly. Like it almost always gets messed up. Is there some principle behind that?
Wait, go back to this thing. Where's the slide? We need the slide. Look. Slide? Where is it? This is very important. This is an excellent question. Look. You said it doesn't scale linearly. You see that? It's a square root.
Thank you.
Hi there, Craig Jones. I'm a staff member and graduate student at Johnson & Wales. This question is for Chef Ladner. I was wondering if you could comment on Dan Barber's pop-up restaurant Wasted that's happening in New York right now.
Yeah, I have not been, but it sounds incredibly interesting. I think it's a really compelling subject, obviously, to address. Dan Barber recently closed his Blue Hill restaurant on Washington Place in Manhattan and started a pop-up, which I believe is supposed to run for a couple of weeks, where he invited fellow chefs, and I know that he also made a menu utilizing only scrap. So a lot of the items that we maybe discard within the course of a day of prepping, especially in fine dining, a lot of times when you're trying to go for specific shapes or stuff, there's a lot of product that gets unfortunately wasted. Cooking as or chef mentality in general teaches us very early on to try to utilize as much of this product as possible. I believe there's a statistic that says 30% of the food produced in the world is discarded before it's consumed. So he's just sort of addressing this issue and trying to come up with creative ways for people to think more about these off compostable or trash bits, and using creativity try to make really interesting food with it. I think I think it's amazing. I can't wait to see what the overall impression is. It's only been in service a couple days, but I think that it's a really important subject to address and to bring to the attention of.
Do you feel that the science behind cooking that we're now coming into as an industry might help lead to more sustainable efforts by chefs, further understanding what we can be utilizing in creative ways?
I think that there's absolutely no discussion that knowledge obviously is power, and if you can practice any of these equations in the course of your normal day, you're only going to improve your food. I don't understand most of it, but I'm interested in learning.
So a lot of these modernist techniques have caught on in especially high-end restaurants, but when people hear about them, especially with the white powders, it's intimidating to a lot of home cooks. I'm curious what your thoughts are on that and what it might take for modernist techniques to catch on a larger scale.
Well, I mean, you cook with white powders. I mean, sugar is a white powder.
Yeah?
So is flour, for that matter, from what I can tell,
true.
right?
It's true.
I mean, you're just not used to xanthan gum. I mean, it's a perfectly natural product. You can buy it in Whole Foods. It's in all of your food anyway. Go look at the food labels on your shelf. And go look at the canned things. There's xanthan gum everywhere. This is just about using it in creative ways. I don't know. I'm not bothered by it, but I'm not a foodie either, and I'm not bothered by it. Are you bothered by it?
No, I mean, it allows food to perform in ways that you can produce more consistent results with potentially less knowledgeable individuals. But I mean, certainly you have to be responsible, and I don't often use powders, as you can tell from the success rate of my experiments here today. But yeah, I mean, they're flavorless in many cases. They're odorless. Most of them are derived from seaweed and other naturally occurring gelling agents. There's really nothing wrong with it.
Thank you.
Hi, I'm Jennifer. I'm a home cook, and I'm wondering if we could go back to the flour. I have two questions. So I'm one of those bad home cooks in that I don't have a scale yet. And I'm wondering if you could explain to us how off you were. Were you off? You did your measurement of the flour in a cup, and then you weighed it. Was he off, or was it accurate? And the reason for my question is I just baked some chocolate chip cookies last night, and so of course I kind of sifted my flour and I spooned it into the 1 cup measuring, and they're flat. And I'm wondering if I had a scale and I was more accurate, would my cookies, they're still delicious, I think, but would they have come out differently, fluffier, taller, not flat and crispy?
Well, I mean,
go ahead.
No, you go.
I mean, when you're talking about packing, taking a dry substance and weighing it by volume is difficult because, I mean, maybe the M&Ms are a poor example, but the flour you could compact and push down, which is obviously going to throw off the weight. In general, I highly recommend that everyone buy a gram scale and convert all of their recipes.
Right, but you have to convert your recipe. I mean, this is the thing. So the problem is, your recipe says, 3 cups of flour.
It cups, yeah.
Right, so that's because your recipe was produced in America and you found it on the internet. But you really need a recipe that basically gives you the amount of ingredients by
grams.
weight, because that's actually accurate. So if you basically weigh a cup, the definition of the weight of a cup is variable. Actually, I'll tell you something else which will scare you. Maybe this will scare you. So we, in the Harvard X thing, we made everybody do 3 experiments as their first experiment. One was to calibrate their ovens, which we did by having people melt sugar, because that was a universal way to calibrate your oven. You just find out at what temperature your sugar melts. The second is we asked everyone to weigh a cup of flour, and we also asked everyone to weigh a cup of water. So it turns out all of your ovens, I could show you somewhere on my computer, I have it, ovens are off by about 20 to 30 degrees. Your oven is off. In fact, if you go and you call up, I mean, how often do you calibrate the ovens in Del Posto? Do you recalibrate?
Hardly ever.
You really?
Yeah. We're just that good. We're just that good.
I see. Okay, I'm surprised actually. So, but your oven is off, but probably you know how far it's off. But it also drifts over time.
For sure.
So the general thing is off by 30 degrees. So your cookies that you cooked, you thought it was at 350 degrees. It could have been anywhere between 320 and 380. So that's statement number 1. Statement number 2, the flour measurements, you saw that. Statement number 3, which surprised me, we told people to weigh a cup of water just as a bit of a joke. Because we figured that, well, it's a cup of water. I mean, everyone's going to, because water, there's no packing problem, it's water. It should weigh 237 grams. And there was a huge width of the distribution. The range was enormous. And so we made a little movie back to the class analyzing the results. And I basically made a joke. And I said, you guys just don't know how to use a scale. And anyway, people got offended. And someone wrote in and pointed out to me that actually that how did I know that the measuring cups are calibrated? Because you actually have a measuring cup, and they have those grader markers on them. Right. And the measuring cups have the property that they go outwards. Yes. Have you noticed that? So that means the last little bit that you put in, the error in that, you're totally... So basically, you think you're measuring a cup. You don't know what the hell you're measuring.
Yeah, it's really
So you
true.
really should use a scale. It's really bad. Like you can't even get the water right, basically. You're not even getting the amount of water right. You have
I'm
no
going to
idea
go get
what
one
you're doing.
tomorrow.
Yeah, so you should, and you can get a new recipe.
It's absolutely worth it.
Isn't that right?
And I can't believe the American cookbook industry still insists on standard forms of measurement and recipes.
I mean, you guys, okay, so I failed on the scale, but you guys in Del Posto, do you do recipes by volume or by weight?
We use a gram scale, and yeah, of course. Yeah. Everybody does. Everybody. Yeah, I don't know a chef that doesn't at this point.
Okay. Next question, please.
Hi, my name is Shivam, and I'm from Brown University. When we use sous vide machines, we're able to cook meat evenly throughout. From the outside to the inside, it's very even. So does heat diffusion work in a different manner in that process, or could you tell us more about how heat diffusion works in that context?
Can I just?
I don't use any sous vide at all, so I don't even really know how to do it.
So can I show you this? So we have on this thing. Can I show you?
I know that the Sears-Oil, for example, was created with the purpose of using it with low temperature cooking. We just did it this way to
the thing is, the sous vide machine will cook the steak to whatever temperature that you put it in the bath. This is a hot water bath that is controlled to some temperature, and if you leave it in, it'll just cook to that temperature.
So doesn't the outside cook more than the inside?
Well, no, because you just leave it there and the whole thing will be cooked. But the problem is that in order to cook a steak, you need to sear the outside, because otherwise there's no browning reactions and it tastes terrible. I mean, go boil your steak and try it.
Okay.
See how that works out for you. But anyway, on this little program that we have, so the best way, I don't know if you'll appreciate this, Mark, the best way so we took lots of different recipes for cooking steak that we found and we programmed them in. So yours we'll have to program in for next year.
Okay.
But we had flip every 15 seconds. That was Heston Blumenthal's method.
Yes.
But the best method, it turns out, is sous vide. But then what you do, this is Nathan Myhrvold's method. You basically cook it in a sous vide bath. You then take it and you dunk it in liquid nitrogen.
And then you sear it.
And then you sear it. And this is what happens. Because it's all right. And look at the end. Look at that. Do you see that at the end? And so you can compare this. Watch this. You can compare two recipes. We can compare sear, sous vide, and liquid nitrogen. That's the final one too. Flip every 15 seconds. And that's terrible, right? I mean, compared to that. So.
Wild.
Hi, my name is Georgina. Do you have any book recommendations about mathematics and cooking or science of cooking or on this topic in general? And a question for the chef. What in your opinion is a cookbook that needs to be there in every house?
A cookbook that what?
That needs to be there in every kitchen.
Every kitchen. Oh, God.
Thank you.
I don't know. You want to answer the first question first?
Well, I mean, I just say for science, by far the best book, I don't know if you'll agree with this, but the best book that I think, I don't want to say has ever been written, but probably has ever been written on the subject is Harold McGee's book on food and cooking.
On food and cooking.
Which is just spectacular, which if you don't own it, you should go to Amazon and own it. And actually,
no question.
It's amazing. And I mean, you know, one thing that we were proud of with the Harvard X class is when the class started, the sales of the book actually started peaking on Amazon because it was, so I mean, that's number one. The other thing is Nathan Myhrvold has really done extraordinary things. I don't know if you agree with this, for understanding the science of cooking. And his books are extraordinarily expensive, but there's a lot of information in them. They're really, I mean, I'm not sure.
He's starting to release them in smaller volumes.
Yeah, but they're still pretty expensive.
Yeah.
And the other thing I would say is there's a book that America's Test Kitchen wrote. I don't know if you, which is called The Science of Good Cooking. Have you seen this one?
Yeah.
It's really a good book.
Yeah.
Anyway,
It's really practical as well.
It's really practical. It's a good book. It's got a lot of stuff. That's right. But now, what about for a chef? I just didn't want to let you.
Well, there's a number of textbooks from Johnson & Wales University that I'm sure you could find really helpful. Some people pay good money for those. There's always The Joy of Cooking. There's, I mean, Mark Bittman's How to Cook Everything. I mean, I'm thinking about stuff that's more practical that you would actually be able to use, for example, on a school night. I don't know, yeah, cooking school textbooks. My friend Cesare Casella recently did a really good book on the fundamentals and techniques of Italian cuisine for the International Culinary Academy that I really like. Yeah, I guess it really, I mean, at this point, it really depends on what sort of food you're interested in exploring because, I mean, there are thousands of books that are coming out every year now, so compounded over the last, however, you know, several decades, there's something for everyone. Yes?
My name's Nina Rooks-Cast. I teach physics and chemistry at Mount Pleasant High School, and I would really like it if you would explain that video clip with the instant freeze.
The instant freeze.
When
Supercooling.
That's super, yeah.
Right, so it turns out that, you know, so it turns out that if you, let me see, how do I explain this simply? So you know, technically if you take water and you, according to the textbooks, if you cool it below 0 degrees Celsius, it's supposed to freeze, right? But and it does freeze. I mean, if you take it and you put it below 0 degrees, it freezes. But it turns out that in order to freeze, there's a process that has to happen in which an ice crystal has to form, and then that ice crystal has to grow to basically fill up the jar. And if you prepare water very, very carefully, it has to be very, very clean, and it has to be in a jar which has no impurities on the outside. And you also use a freezer which is very well temperature controlled. So it's not like the freezers that you have at home. It's actually a good...
Like medical, cryogenic.
Yeah, a good freezer. And you sort of, it turns out you can get water, you can cool it to below the freezing point of water and have it sit there in a state which is not stable, but it will be in liquid state. And if you then take it out of the freezer and you pour it on anything, as soon as it touches anything, it freezes. And that's what you were seeing. And scientists call that supercooled water. And actually, this is a topic that is more or less a topic in ICERM's workshop this week, at least in some way, abstract way. I think this appears. And so it's a good question to end with, since ICERM sponsored with Johnson & Wales this lecture.
Thank you all for coming. Safe travels home, and let's give these chef scientists another round of applause. And I'd like to thank the staff of Johnson. I'd like to thank Johnson & Wales and ICERM staff
and his staff and all the support of the culinary campus today, helping us get all this together. Super organized and made it really easy for us all. So
yeah, you guys were amazing.
I appreciate that. Yeah, thank you.